All right. I'm very pleased to welcome all of you to our annual SLAC lecture. The SLAC lecture is named in honor of Francis Slack, who was effectively the founder of the modern Vanderbilt physics department. He worked here for many years. His main scientific contribution was a confirmation of the existence of nuclear fission around the time of World War II, and then he held a variety of administrative posts at the university after that. And we're very pleased to welcome today Freeman Dyson. If I gave you a complete rundown on all of his achievements, that would take a full hour, and there's no time for him to say anything, so I won't do that. I'll just mention briefly, he was born in England. He attended Cambridge University. During World War II, he worked for the Royal Air Force, doing operations of bombing missions. He came to the U.S. after the war and held positions at Cornell University, and then he's been employed at the Institute for Advanced Study in a permanent position since 1953. He was influential in the development of quantum field theory. He showed that the different formulations that were current at the time were actually the same theory, and he popularized the use of Feynman diagrams. He's made numerous contributions to pure mathematics, especially random matrix theory. He suggested the idea of the Dyson sphere for civilizations to capture all the energy of their sun and not just a little bit of it. He's the author of 10 popular books. His most recent mathematical work, a couple years ago, he wrote a paper with Bill Press on a new approach to the prisoner's dilemma, which got a lot of publicity. He's a member of the National Academy of Sciences, a fellow of the Royal Society, the winner of the 2000 Templeton Prize for Science and Religion, the winner of the 2012 Poincaré Prize for Mathematical Physics, and the most impressive thing about him is that he does not have a PhD.
Well, thank you, all of you who had any hand in inviting me here. I'm sorry it's such a brief stay. I only got to meet only a few of you. So anyway, that's it. And I'm talking about ancient history. I'm here mostly as a historical monument, but still, life is good, and I'm still more or less alive and kicking. And so the four things I wanted to talk about are four revolutions which just by amazing chance all happened at the same moment, just as World War II came to an end. And these were space, nuclear, genomes, and computers, all four new technologies which created new branches of science. And so it was amazing luck just to come on the scene at that moment. So I'll talk about roughly 15 minutes. I don't have a watch, so you better tell me when the time has come to shut up. Try to spend 15 minutes on each. The first was space, because I was in London in 1944, and the V2 rockets began coming down from the sky. And that we were absolutely delighted with that, because it was a unilateral disarmament of Hitler's Germany. It was these rockets were, from a military point of view, they were completely irrelevant. They were killing a few people once in a while in London, having absolutely no effect on the war. The Germans were desperately in need of airplanes, especially fighter airplanes, to defend their armies and to defend Germany. And every V2 rocket was essentially equivalent to a fighter airplane in technology and cost. So this was a fundamental strategic mistake on the part of Hitler. We actually found out later, talking to Wernher von Braun, what happened. Wernher von Braun, of course, invented the V2, and his purpose was to go to Mars. And he hoodwinked Hitler very successfully. He promised that he would have this wonderful new weapon system. And Hitler actually asked the right question when von Braun showed off the V2 rocket to Hitler. And Hitler said, "How many of these can you make?" And he said, "I know what artillery is all about. This is just artillery, it's nothing more. And if you want to win a battle with artillery, you need millions of shells, not just thousands. Can you produce millions of these rockets?" And von Braun said, "Ja, mein Führer." And Hitler never asked any further, and of course he never produced more than a few thousand. So from a military point of view, it was totally meaningless. Anyhow, it was very important for getting to Mars, and of course we welcomed von Braun after that, and he became the leader of the American project, as we all know. And it was a great time for those of us who were excited about space. I mean, we could see immediately Arthur Clarke, who was then a young man writing science fiction and also working for the British communications, and he invented satellite communications. He took out, I think, a patent for the first communication satellite, and he had all the right ideas about space. Essentially, it's the problem of communication, which turned out to be true. And he also wrote very good fiction. Then there was a long wait, and we were sad to see nothing much was happening for about almost 10 years, that nothing seemed to be happening in space. And then, of course, what was actually happening was the military was developing rockets, including von Braun on our side, and Korolev, who was the equivalent figure on the Russian side. And then finally in 1957, what was it, 57, yes, the Sputnik went up. And that was a great event for everybody if you were excited about space. Suddenly, space became fashionable, and it became possible to get money for all sorts of crazy schemes. And a friend of mine, whose name was Ted Taylor, had a crazy scheme for getting into space with nuclear energy right away. And instead of doing Apollo, which is the old-fashioned chemical rockets, we would use nuclear bombs right away and get to space far more cheaply, far more efficiently, far more effectively. And so we had what we called Project Orion. And in those days, you could actually get money for that sort of crazy stuff. And so we got money, first of all, from the Advanced Research Projects Agency, which was at that time not yet DARPA, it was ARPA. So it didn't have to do defense. And so we got money from them first. And then, meanwhile, von Braun got his money from the United States Army. So we were in direct competition with von Braun to get to the moon. But we could do much better. We could get to Mars quicker than he could get to the moon. So we said. So for about a year or so, it was a real race. And something, I had the feeling we really were going. I really was intending to fly. And Ted Taylor, of course, was in charge. He was even younger than I was. Everybody in those days was young. That was, it was true of Los Alamos. Most of these wartime projects were like that. People were having the best time of their lives doing all sorts of horrible things. And Orion was exactly like that. So we had a bunch of people in San Diego in a little red schoolhouse working on this project. And it was delightful because you didn't have to worry about who you were, whether you had a PhD or what. They were engineers and chemists and physicists all working together. And it didn't matter who thought of it. It was just a question, can you really get this damn thing to work? And that was what it was all about. We had not only calculations, which of course was mostly what I did, but we had also engineering development, actual models of parts of the ship. And we also had little flying models, which weren't really models, they were just toys, but just to understand the control problems. And that was great fun. Every Saturday, we didn't actually get paid for that. We all went out on Saturdays on our own time, to do these toy model flights, which were, of course, not really officially part of the program. So we had little chemically propelled explosive rockets with which 6 1-pound charges of high explosive to go bang, 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 and up to about 500 feet or so, and then float down with a parachute. And they worked very nicely. So we learned how to actually do the steering, do the control, get the explosives to blow up at the right moment, to the proper timing of the explosives. So all that we could do, and the amazing thing is we never got hurt. We were handling hundreds of pounds of explosives, and in those days, of course, the rules were very much less strict than they are today. And I think actually the explosives weren't even bought, they were stolen from the Navy. And so then after about a year, we were ready to go. And it was then a question, well, if you really wanted to do this, you had to have a nuclear test. You had to have a pusher plate. The ship was a big round dome with a flat pusher plate at the bottom. And the idea was that the bomb would go off 100 feet below. The debris from the bomb would hit the pusher plate and with a very strong pressure pulse and lasting about a millisecond. And the pusher plate then would move upwards, and if all went well, you'd have a set of shock absorbers which would transfer the momentum from the pusher plate to the ship. So we designed the shock absorbers, and then above that you'd have the passenger compartment and the recreation rooms and everything else, and a big sort of Coca-Cola machine for handling the bombs. It was actually designed by the Coca-Cola company, and you had a big rack with about 1,000 bombs on it, and so you had to move them around to be sure they were in the right place when they needed to go. Anyhow, so we were ready, except we didn't have a nuclear test. You had to have some sort of a big underground space with a pusher plate on one side and a bomb on the other side, actually explode a real bomb and see how a real pusher plate would behave. And until you'd done that, nobody would believe a word you said. And so it was a problem. We had to get permission to do this nuclear test. And that never happened. And of course, there were all sorts of reasons, but it was just politically something nobody really wanted to sign off on. It was just politically too many problems, or the problem of radioactive fallout, problems of handling of bombs, problem of security clearances, and all sorts of details. So there was always some reason or other why the papers never got signed. Meanwhile, of course, von Braun was moving the big battalions ahead, and his program won. And we were good friends. Actually, he supported us. He was very friendly to Orion because he realized we weren't a serious threat. And so then there came an interesting time when this was 1963, when the test ban treaty came up, and when Averell Harriman went to Moscow to negotiate with the Russians. And of course, by that time, the whole political atmosphere had changed. Linus Pauling had done his work very well, alarming the public about fallout, and Linus Pauling was a real hero and persuaded the public that fallout really was a problem, and we were poisoning the milk for our babies. And so it became then a big political question: why not stop the bombing, stop the bomb tests? And so there were two possibilities: either a total bomb test, which is what we wanted, or atmospheric bomb test ban, which was what we got. And so Harriman went to Moscow, and we offered, by that time, I was then a peacemonger, and I went to the Disarmament Agency in Washington, which was a wonderful place at that time. This was during Kennedy administration. The Disarmament Agency was really a new thing. It was set up so to be the counterbalance to the Defense Department, we were supposed to wage peace while the Defense Department was waging war. So it was very big hopes for this disarmament agency. It was still very small. So I went to work there and helped with the test ban treaty. So we offered to help Harriman when he went to Moscow to provide technical backup and support for his negotiations. And he said, no, for heaven's sake, don't send scientists. And if you want a treaty, keep them out. And of course, he was right. And so in 3 weeks, he had a treaty. And it was only for atmospheric tests, but still, it was better than nothing. And it has worked extremely well. So that test ban treaty was the death warrant for Orion, of course. It meant that Orion still existed at that point, but it was then, after the test ban treaty, it was clear that it would never fly. And I had a wonderful, just by chance, another kind of history was taking place just the same day. That was actually while this test ban negotiations were going on, and I was at the disarmament agency. Martin Luther King came along with his march on Washington, so I just walked out of the door and joined the march, and it was a wonderful experience, of course, seeing history made, and Martin Luther King giving his famous speech, "I have a dream, I have a dream," and everybody was weeping. It was really quite amazing. And so those were stirring times. And after that, of course, space went on its way, and it became half and half. It became, on the one hand, a huge success scientifically. The unmanned space program was wonderful, and it remained wonderful. Just now we have the Kepler mission, which most of you probably know about. Kepler mission is a very simple mission, it's now finished, staring at a small patch of the sky with very, very accurate photometry. So you can actually measure planets coming across in front of the stars, and it's looking at millions of stars. And so it's a wonderful example of what you can do with the modern detecting equipment. These optical detectors are just amazingly precise, something like noise level of 10 to minus 8 or something of that kind. And so it can measure these tiny diminution of the light as the planet goes by the star. And at the same time, of course, it has this broadband communication to the ground, so that you can handle all the data from millions of stars. So they've discovered already about 2,000 planets just with that one instrument. So it's completely transformed our view of the planets in the universe. That planets, in fact, are as common as stars, or in fact, commoner. There are more planets than there are stars. And we've not only discovered that they're there, we've discovered a lot of information about them. You can measure their radii from the form of the transit. You can also measure the masses in case there are more than one, and you see them interacting with each other. And you can do all sorts of quite accurate measurements. So we're learning a lot, not just about our own solar system, but about planets in general. That's typical of the way the space program goes, that the small missions are often just as important scientifically as the big ones. Big ones, of course, get all the publicity because they cost money. But anyway, the space program is roaring ahead, and of course the Europeans are doing extremely well, so are the Japanese, and China is coming up. So it's going to continue, and it is certainly a very good way to do science, combined with ground-based astronomy. And of course, there again, very often the credit is given to Hubble for things that are done on the ground. We're accustomed to that because Congress, of course, has to pay a lot of money for Hubble. They don't pay so much for telescopes on the ground. And the recent triumph of measuring the microwave background polarization, of course, was done with a telescope on the ground. Quite cheap. It's a marvelous operation. It's a telescope at the South Pole. And I mean, it's really amazing how these people get things to work at the South Pole. Again, with unbelievable precision. I mean, this microwave background radiation itself is only varying by 1 part in 10 to the 4 from point to point in the sky. And that's the total anisotropy that they're measuring. And then they're measuring the polarization, which is another factor of 100 less. And still they get high precision. It's a wonderful achievement. And the press, of course, considers that's answered all the questions about cosmology, which is not the case. But it is true, it's raised a lot of questions, and that's what science is all about. It's raising questions more than answering them. So let's talk a bit about nuclear. No, I'll just finish with space, because there's the other part of space, of course, is the manned program, which is very, very different. We had a 10-year manned program to go to the moon, and it was announced by Kennedy as a 10-year program, and nothing to follow up. So it was guaranteed to be dead on arrival, and which is what it was. It was very sad. It was not the way to do a manned program. A manned program ought to be for centuries. It ought to be planned from the beginning to be long range, something that's not going to be done quickly, and that was so it was completely wrong for a manned program the way it was done, which means we lost 50 years as a result. That after Apollo there was nothing to follow, and in fact it was actually discouraged anybody from trying something like that again. So it was really a disaster for manned spaceflight. Fortunately, this is now gradually recovering, and now we have little companies going up into space, and there's a good chance there will be a revived manned program, which is much more long range, and with small enterprises competing, which are not too big to fail, and so they can afford to take risks. And I think this has a very bright future, but it will be then sporting events and not science, and that should be clearly understood. That was, of course, not understood with Apollo was sold to the public as science, when really it was a sporting event, and that was a big mistake. So second revolution was nuclear, and that, of course, hit us as a miracle. I was in England at that time, and we suddenly opened the newspaper one morning. It was the News Chronicle, which was one of the English papers, and there was a huge headline on the front page saying, "New force of nature harnessed." And it was big stuff. It wasn't just a battle in the war. It was a real change in history, and new force of nature harnessed. And so that was the way we felt right there. And this was a big, big deal. And so we thought this was going to be the future, and of course we were wrong. And so that was the revolution that failed. It has never done what it promised to do, either for science or for the human welfare. But still, from a scientific point of view, it's been helpful. There's a lot we've learned, of course, from nuclear physics and particle physics. It's good science, but it's certainly been a total flop as far as human welfare is concerned. And of course, I spent a lot of time on that. I was as enthusiastic as everybody else. On that day in August 1945, when the bomb dropped on Hiroshima, I was all set, in fact, to fly to Okinawa. The Royal Air Force was going to send a fleet of bombers to be based in Okinawa to help in the bombing of Japan. And I was going to fly with those boys to Okinawa. And we had we weren't told about nuclear weapons, of course, at all. We were intending to continue bombing Japan into the indefinite future, and it looked pretty grim. it was easy to imagine the war with Japan would go on for another 10 years. Anyway, the bomb, we were just amazingly delighted that suddenly the war ended, 2 bombs, and that was it. Of course, now we know that it wasn't that simple. That there's recently a book written by a friend of mine called 5 Illusions About Nuclear Bombs or Nuclear Weapons. His name is Ward Wilson. I recommend the book. This is a commercial, by the way. So Ward Wilson has studied the history of why Japan surrendered. And it turns out, if you look carefully, that the real reason they surrendered had nothing to do with the bombs. It was actually because of the Soviet invasion of Manchuria, that the Japanese military could not fight a war on 2 fronts. They couldn't have defended Japan from the Americans in the south and from the Russians in the north. And they knew that. So it was a deliberate choice of the military to surrender to the Americans and keep the Russians out, which is, of course, what they did. And when the emperor gave the order to surrender, he was not at all sure that the soldiers would obey. It was in Japan, of course, it was very, 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 very deeply frowned on to surrender to anybody. And so the emperor wasn't sure anybody would pay any attention. But he sent his message to the troops, which contained the real reason for surrendering, which was the parallel with his grandfather Meiji. Meiji was the great Japanese emperor who modernized Japan, who was the grandfather of Hirohito. And Meiji, in 1895, won the war against China. There was a Sino-Japanese war in 1895. Japan won and took over Manchuria, and then the Russians intervened, and Meiji then surrendered to the Russians, and the Japanese swallowed their pride, gave back Manchuria. And so that's what the great emperor did in 1895. That's what Hirohito actually said to his troops, that this is what my grandfather did, and this is what we have to do. And you'll see in the end it'll turn out all right. And so that was the argument he made. So it was to keep the Russians out. In both cases, it was necessary to give up the fruits of war. Anyway, so that was the real motivation for surrendering. Afterwards, of course, they gave the bombs as an excuse. It was much more acceptable to the Japanese public to say we surrendered because of the bombs. So it was a certain amount of double talk, of course, afterwards. But I think the history is fairly clear. So the bombs didn't actually even end the war. And of course, so all the other promises that were made turned out to be falsified too. But we had a good time with nuclear energy. So I also helped to build a peaceful nuclear reactor called the Trigger, also in San Diego, with the same company that did the Orion program. The company is called General Atomic, and so Trigger stands for Training Research Isotope General Atomic. And so that was the name of our reactor. And the interesting thing about that reactor is that we did it right, that our leader was Edward Teller, who is, of course, well known as the inventor of the hydrogen bomb. But in addition to that, he was also the great proponent of reactor safety. He was the head of the Commission on Reactor Safeguards. So he was actually equally fanatical about hydrogen bombs and also reactor safety. And so he was the leader of this project, and he said the rules are very simple. A reactor is safe if you can give it to a bunch of high school kids to play with and they won't get hurt. And so that was the criterion. And so we built the reactor by that criterion. And the way we tested it was just to do the worst possible accident. And that's what you have to do if you really want to be safe. So the worst possible accident we calculated was you start cold with because it's a water-cooled reactor. So you start with the water cold and the core cold, and you pull out all the control rods as fast as you possibly can, let the thing go supercritical, and nothing happens. That's the criterion for being safe. So that's what we did. And of course, we didn't do it the first time with all the control rods. We did it a little bit at a time, but each time a little bit more. We did about 1,000 tests like that. And the last time, actually, we got Niels Bohr himself, the great physicist, to come to San Diego, and he pulled out the control rods at a public ceremony to demonstrate the safety of the reactor. He was very much pro-nuke, like everybody at that time. He thought that nuclear energy was the great thing for the future. And anyway, so the reactor actually worked, and it sold. We actually sold to 75, and they've never given any trouble. They've done very well as far. But it's of course a small reactor. It's 1 megawatt, and so it's not a producer of electricity. It's for producing isotopes, mostly for medical purposes. Mostly they were sold to hospitals, and a lot of them are still producing. But unfortunately, the reactor industry did not follow our good example. Instead, they followed Admiral Rickover. And Admiral Rickover, of course, was our competition. He was building reactors for the Navy. And he, unfortunately, was building reactors for submarines. And, of course, submarines impose big constraints. The most important thing about a submarine is there's very little space. So you have to build everything as compact as possible. And so submarine reactors are necessarily very compact, have very high power density, which means they are inherently unsafe. And there's nothing you can do with a submarine reactor which really makes it safe in Teller's sense. It was good in the hands of the Navy, because the Navy can actually do things sensibly, and they can train people well. And so the Navy actually works these reactors very nicely. They've never had any accidents. And it's so from their point of view, it was a success. But unfortunately, the civilian industry, when they started building nuclear power reactors, took the Navy design as the standard. And since the design existed, then they wrote the regulations so that essentially that's the only design you can use. So the present generation of light water reactors essentially is Rickover's idea, just made a lot bigger, but it's still inherently unsafe in the sense that, as you see in Fukushima, if you cut off the power while they're running, they will melt down. If you don't do anything to stop it, they will melt down, and unless you have a working cooling system after the shutdown, you're in trouble. And of course, the Japanese unfortunately didn't talk to the tsunami experts when they put those reactors by the seashore. And you'd think, I mean, Japanese, after all, invented the word tsunami. You'd think that they might take that seriously, but they unfortunately didn't. And so anyway, it's been one damn thing after another. And there's a lesson about all these accidents, which I find is quite universal. I've looked at a lot of accidents, and there's one very good one, which is the Ocean Ranger, when a huge oil platform capsized in the Atlantic. That was about, 30 years ago. It was interesting because it was an American platform with a Canadian crew, and it was operating off Canada. And so they had two commissions of inquiry after the capsizing. one American and the other Canadian. And so you got both reports. And so you know actually more about what happened than any of the other accidents. And it's a wonderful drama. I mean, it's a terrible tragedy. Everybody on board drowned. And it was about, I think, about 150 people drowned. And it was an absolutely typical accident. There were two groups of people on board, the tool pushers and the mariners. The tool pushers worked for the oil company. The mariners worked for the platform, and they didn't talk to each other. Of course, the tool pushers knew how to drill for oil, and the mariners knew how to operate the ship. And you'd think that in case of a big storm, the mariners ought to be in charge, but that wasn't so. Of course, when there was a big storm, it turned out the tool pushers were in charge, and they didn't know what to do, and they gave all the wrong orders. And so in the end, they succeeded in, which was almost impossible, to capsize the whole thing. And then there were it was one disaster after another. But it's a basic lack of communication. And afterwards, they played tapes of the chief tool pusher talking to the mariners and telling them what idiots they were. And it was horrible just to listen to this guy talk, and that's the way it is. And it was the same, I'm sure, in Fukushima, that you had the people in Tokyo who were in charge and gave the orders and had no idea what was really going on. And the people in Fukushima who actually knew what was happening but didn't have the authority to do it. I should mention, perhaps, in that connection, how's the time going? Okay, I should get on. But I'd just like to mention Feynman. Feynman, of course, the great physicist, was on the Commission of Inquiry for the shuttle accident. When the O-rings were burned through, and because the temperature when they launched was too cold. And it was Feynman who understood what the problem was and explained what happened. And he said he actually talked to the people who were operating the launch and the people who were in charge at the NASA headquarters and asked them what was the probability of a failure. And he got two completely different answers. From the people who were on the site who actually were doing the launch, they estimated the failure rate at 1 in 100. So that's historically roughly what it was. And so expected they would lose about 1 in 100. The people at the NASA headquarters said 1 in 100,000. And that was based on nothing but politics. You know, they had really had no idea. It was policy that was safe. And so for political reasons, they had to believe it. And that was how it was. And that's the problem with all these big projects. That the executive is in the hands of these managers who are far away and have no idea really what the risks are. And the people who do know the risks have to do what they're told. So it's a very general, the same thing happened in Chernobyl. There you had two groups of people. You had the electric power people who were trying out the power system, and there were reactor people who knew how to operate the reactor. Exactly the same problem. They couldn't talk to each other. And of course, the power people were in charge. And so they said, let's turn this safety systems off, see what happens, and blow up it went. And anyhow, the third revolution is genomes. That's, of course, another world entirely, but very, very exciting. And that's a case where, again, the human benefits have not been achieved. We all believed that once you knew about the human genome, it would revolutionize medicine. You could cure all kinds of diseases. Well, that has not happened. We have the genome, but we still can't cure cancer. However, we have done a lot of really good science, and the genome, of course, is wonderful for science. And just now, there's this beautiful piece of work of Svante Pääbo. I just read his book, what is it called, the Neanderthal genes, I think it's called, the story of how they sequenced the Neanderthal genome, which is an enormous scientific achievement and not at all straightforward. But the price of a genome has come down in 10 years from $1 billion to $1,000. That is quite a remarkable shift, factor of 1 million in price. And so it means now genomes literally are cheaper than you can, I mean, it's cheaper to sequence a genome than it is to read it after you've sequenced it. Reading it costs more. And so genomes are essentially free. And, well, of course, that has been a wonderful chapter in biology, and I had a modest part in that. I tried to, because Francis Crick was the leader of the genome revolution. He was the one who discovered, with Jim Watson, the double helix structure of DNA, which was the key to the genome. And I happened to be a friend of Francis Crick during the war when we both were working for the government. He was working for the Navy and I was working for the Air Force. We actually met from several times. And he was totally depressed. He was 5 years older than I was. So the war had hit him at the worst time when he was just at the beginning of his professional career when the war began. And so he was out of science for 6 years and totally depressed. He said, yeah, I'll never amount to anything as a scientist. I've forgotten everything I learned. And he was just in a bad mood. And anyway, he said, well, maybe he had been trained as a physicist. He said, maybe I'll just make a completely fresh start and switch to biology. And I said, no, don't do that. And I said, you'll be too old. It's true that biology will be exciting later on, but not yet. Physics will still be the most exciting for the next 20 years. So by the time biology becomes exciting, you'll be too old. So you better stay in physics. And fortunately, he disregarded my good advice. And anyhow, more recently, there's been some wonderful work by a man called Stroessler, which is not so well known, but maybe I might mention it, which is what I consider perhaps the next big revolution, which is neurology, or the whatever we might call it, paleontology, the science of human origins. Anyhow, so what did Horstler do? Horstler is one of the new brand of biologists who never got his fingers wet. He's actually trained as a computer expert, and all he does is read genomes. He never actually sequenced one, and but he knows how to read them. And anyway, so Horstler had the idea of looking for pieces of genome which are specifically human, and that he might find something interesting. And so he took the genomes of 6 species, which by that time were all available: the chicken, the mouse, the rat, the chimpanzee, the dog, and the human. And you got all 6 of those. And he looked for pieces of DNA which were absolutely identical all the way from chickens to chimpanzees, which meant 300 million years roughly from the common ancestor of mammals and birds all the way to chimpanzees. There had been no change. So it meant this piece of DNA had to be doing something very essential, so it couldn't change, evolutionary speaking, all the way from chickens to chimps. And then between chimps and humans, it had big change. 18 mutations. So it must have changed its function drastically between the chimps and the humans. And he found that there are actually two pieces of the genome, which he called HAR1 and HAR2. HAR means human accelerated region. And so there they are. And I mean, the first thing to say about them is they're not genes. Neither of them codes for protein. So they're simply unknown function. They're pieces of DNA which are doing something obviously very important. We really haven't the foggiest idea what they do, but they must be controlling something very vital. And so there are two other facts which he discovered about. The first is when they're active, you can tell by looking at mice at various stages of development when these genes are switched on. And it turns out it's in the second trimester of pregnancy, which is what you would expect. They are active just when the main organization of the human body is being laid down between 4 months and 6 months in embryo. And so it's the time when the main structures are being organized. And then the question is, where are they active? And there you can guess beforehand where they would be most important to be for making human beings. And it turns out HAR1 is the cortex of the brain. HAR2 is the wrist. So those are the two parts of the human which make us different from chimpanzees. And anyway, so there it is. And now we still have to find out what those pieces of the genome are actually doing. But I think this is probably the start of the next big revolution, that when we can understand what this kind of control machinery really does, and we understand then really what it means to be human. Well, the last revolution is computing, and of course that's the one that actually did best of all, and quite unexpectedly. I mean, we all knew that computing was big, but we had no idea how big. And it was, because it started with Turing, 1936. He wrote this wonderful paper on computable numbers. And I remember when I was a student of mathematics, and I happened to hit this paper of Turing, just browsing in the library in Cambridge. And I thought, what a marvelous piece of work. It's just so beautiful piece of work, sort of describing in abstract terms what computability really means. And I read this whole paper and thought, oh, how beautiful it is. I never had the faintest notion that it would actually be useful. And it was never nothing in the paper suggesting that it might be useful. And I don't think even Turing understood that at the time. And anyway, then after the war, of course, computing really took off, and von Neumann started the project in Princeton, which I wasn't directly involved with, but I was very much a friend of the family. And it was great fun watching this machine actually emerge. And of course, it's quite astonishing. When the total memory in that machine was 4 kilobytes. And what you could do with 4 kilobytes was quite amazing. And because they had everything was programmed in machine language, of course. But what von Neumann understood was just that programming was what it was all about. He didn't invent computers. What he invented was software. And software was, in fact, the big step. And so with software, you could do amazing things with 4 kilobytes. So there was a young man called Barricelli who did simulated evolution, which was really astonishing. He had populations of creatures evolving and learning how to become parasites and prey and symbiotic combinations and so on, all inside 4 kilobytes. And it's absolutely beautiful, but his Barricelli was totally ignored. think the biologists never read his papers. It all had to be rediscovered 40 years later. But anyhow, that kind of thing was going on. And, well, of course, now we're in this new age where what's the time now? 10 minutes. Oh, well, then I don't need to rush. Now, of course, we reached the critical point about 10 years ago when it became cheaper to store information than to throw it out. And that was sort of a turning point. So after that time, nothing ever gets discarded because it would be too expensive to discard it, and so you just store it. And so we're drowning in a swamp of information. And so that's what science is now doing. Not only science, it's interesting that it's arrived at the whole civilization is faced with the same problem. It's not only scientists, but historians, and there's Google, of course, and all kinds of industrial businesses which use huge databases. And in the end now, the genome turns out to be rather small compared with these other databases. It's amazing how efficient the genome is. It's 3 gigabytes, essentially, the human genome. And most of the species are smaller than that. So the entire living world, the living planet that we live on, is just about 1 petabyte. If you could sequence the whole biosphere and everything that's living, that's going to happen pretty soon. That will take about 20 years at the present rate of growth. I mean, of course, now sequencing has got so cheap, the limiting factor is not sequencing anymore. It's a question of who's going to use it and who's going to store it. But anyhow, so we shall have the genome for the whole planet in about 20 years. So that's going to be another revolution. And that again ties up with space. So I like to look at the future of space on a bigger scale, more like the Russians look at it. It's not a problem of human beings, but it's a problem of life as a whole. That here is life, as far as we can tell. Life is just stuck on this tiny little piece of rock going around the sun, and everywhere else we look, the universe is dead. And we've listened very hard for radio signals, heard nothing. It seems there really are very few intelligent aliens in our neighborhood anyhow. And so the question is, what about it? When is it going to happen that life will move out into all this great universe where it could be? And so I think that to me is the most interesting question for the future. And so I like to think of this in terms of the transplanting an ecology. You're not transplanting a species, you're transplanting a complete ecology, a biosphere, or whatever you like to call it. But that's now something you can think about in fairly concrete terms, that what would it take? Something like an ostrich egg weighing a couple of kilograms or so could contain easily enough DNA for the whole biosphere of this planet many times over. I mean, not just DNA, but a lot of life support and other things to go with it. So you could imagine this little Noah's Ark egg going out and exploring the universe, looking for a place to settle down. And why not? And I think it's very likely it's going to happen. And it's something I could imagine would not be all that expensive. Certainly, quantity of data is something we can deal with. It's much less than Google deals with every day. And the propulsion is not all that difficult. If you're talking about a few kilograms, you can get it going pretty fast. You could certainly imagine going out further than the solar system if you wanted to. And even the solar system is quite big. So anyway, I see that as definitely in our future. So it's not just us that's going, but everything is going. And of course, the question is, what does the universe actually look like? And there's a very nice little book which I'm fond of, which is not widely known, which was written by the Russian Tsiolkovsky. Konstantin Tsiolkovsky was a Russian schoolteacher. He was the real pioneer of space, because the Russians have given him all the credit for that. If you go to Baikonur, which I did recently, which is the Russian launch site, there's the Holy Trinity there of space as seen from Russia. The Holy Trinity consists, of course, of Tsiolkovsky, the prophet, who foretold everything that happened. He was writing in the 19th century. And then there is Korolev, the great engineer, the designer of Sputnik and the designer of all these great Soyuz launchers and so on. And the third, of course, is Gagarin, the first man who actually traveled in space. So they're all Russians, and so they're very proud of that. And so I feel with some justification. Anyhow, so I see the future as being somewhat like that. That we will go not just by ourselves, but with this entire ecology of living creatures. And when you read that little book, this little book of Tsiolkovsky, which is called Dreams of Earth and Sky, which is a very nice title, and it's sort of a mixture of science and science fiction. So he's having conversations with the aliens on a little asteroid, and the aliens are telling him, well, why do you live on a planet? What's the point of living on a planet? It's the most inconvenient place. Have all this tremendous gravity, it's getting in your way. You have an atmosphere, which means that you're dissipating energy every time you move around. Why not go to a small asteroid? That's much more convenient. And so that's the argument. And so and Tsiolkovsky, of course, agrees with the aliens. And that if you go to a small asteroid, you have three problems. There's zero G, that's zero gravity. Well, that's a medical problem, but because we don't yet know how to solve it, but it's fairly clear you will be able to solve it once you know how things work. And then second problem, of course, is zero P, zero pressure, living in a vacuum. That means some biology. And the third problem is zero T, zero temperature. Most of these places are very cold. And so anyway, you have to imagine these creatures biologically designed. As Tsiolkovsky said, it's not a problem of engineering, it's a problem of biology, how to live in space. And I think that's right. And so we will see, well, as soon as we understand the genome really in depth, we can design creatures that live very comfortably in space. And we'll be very happy with our fur and our impermeable skin and our green wings. They carry, these aliens carry green wings which absorb sunlight and process chemicals so they don't need to breathe. And that's how we will be. We will be running around on the asteroids like that. And anyway, if you look at the real estate in the galaxy, almost all of it is small objects. Planets are actually a very small part of the real estate. So the real estate is measured by area, not by volume. And so the place where life really will flourish is probably this small, cold places. And of course, once you're out there, you can move so easily from one place to another. You're much more convenient. You're mobile. you're free then to travel anywhere you want. So anyway, that's enough. Thank you.
quantum field theory, billions of dollars spent to find the Higgs particle. Astrophysicists are worrying about how stars are made. And physicists always close their eyes to biology. That's not for us.
So, well, it's of course not true anymore. Now there are very large numbers of my physicist friends switch to biology. It's becoming easier and easier, of course, since essentially the tools are the same. They're both in biology and in physics. You're just essentially dealing with large databases, and so it's easy to switch. It's also fairly easy to communicate across the disciplines. So I think that's a problem of the past, not of the future.
So it was too hard?
No, it's just now become much easier.
Do you have a personal favorite answer for Hawking's paradox of if there is intelligent life out there, why have we yet to encounter any?
Well, it's Fermi's paradox, not Hawking. But anyway, no, I think it's likely that life really is rare, and I don't know why, but it seems to be true. Yes.
So we hear sometimes people talking about manned mission to Mars nowadays, right? Is there any chance that we can revive the Orion project and just look here try to accomplish that?
No, I wouldn't want to do it even if I could. And I mean, there are very good reasons for not doing it. First of all, it causes a huge radioactive fallout. That was the immediate reason for not doing it at the time. It's still a good reason for not doing it today. And the other reason, of course, is that we don't need 1,000-ton payloads. We wouldn't even know. We wouldn't know what to do with a 1,000-ton payload if we got one for free. Yes.
For all of these revolutions you've described a promise both for science and for the human welfare. But this paleo-neurology revolution, which you see coming in the future, what is the benefit for the human welfare that you think it might have?
Well, I would say understanding what it means to be human means understanding our minds. I mean, it's our minds that really make us different from chimpanzees. And so we have no idea how minds work. But I'm sure when we understand that, it'll have profound consequences. I mean, it could be bad as well as good, of course, like everything in science. But understanding the mind in some practical sense would have huge consequences. I mean, maybe we would all become geniuses, or maybe we would all become idiots. But one way or another, it's going to change the way we think of ourselves.
Professor Dyson, when we modify ourselves to live in other environments like the asteroids that you mentioned, and we've increased our lifespan so that to make it more convenient, will we still be human?
Well, that's a matter of definition, and scientists are not supposed to make definitions. That's for lawyers.
Question here. One of the estimations you have to make when discussing the Fermi paradox and how many intelligent civilizations there are is the lifetime of the civilization. And some of the more pessimistic outcomes say that once a civilization discovers nuclear technology, they might blow themselves up and never reach the stars. I guess, based on your thoughts about us traveling to Mars and beyond, What makes you so optimistic that we're going to make it?
Well, I would say I'm optimistic just because that's in my nature. And growing up in the 1930s when things were much worse than they are today, and we somehow survived the 1930s. So I guess we'll survive. But anyhow, as far as the argument about the lifetime, I don't see that the lifetime is likely to be always short, because once you get out in space and if you're traveling freely from one place to another, you really are invulnerable. And local disasters won't extinguish the species anymore. And so it's essentially a question, do you develop your super bomb and blow yourself up, or do you start space traveling, and whichever comes first determines your fate in a way. And so that's a very simple argument, but I think it's roughly speaking true. As soon as you become mobile in the galaxy, then you're going to live long, and you'll have descendants going all different places. So I don't see it's likely that any species that once reaches that point will ever die out. What will happen, of course, it will diversify and evolve, and it will become different. And your descendants won't be human anymore, but so what? And they probably feel nicer the way they are.
In your first two revolutions, you described a sort of way that unhealthy competition led to a suboptimal result. You know, trying to get to the moon in 10 years led us not to sustain the effort, and then two competing reactor systems led to that result as well. How do we form a way to organize what we're doing so we get something sustained, as opposed to no result from a genome, no new medicine, etc.?
Well, there's no magic, of course, to technology. I think the experience is that if you try to predict what's going to win, you'll always guess wrong. And so that the thing to do is, as far as possible, have a level playing field and let all the different schemes compete with each other. And that's what did not happen with the nuclear industry. They set the rules much too quick and much too rigidly. And generally speaking, the industries, which the computer industry, of course, really took off when it went in the direction of microchips and becoming smaller and smaller instead of bigger and bigger. That usually seems to happen. I mean, if you can get things smaller, it goes faster and it becomes much more competitive, and generally things work. So that's as a general rule. It doesn't always happen, of course.